Don't forget to subscribe, comment and like. Welcome. Welcome. Today we want to look at how to balance chemical equations and how to write correct chemical formulas. So I usually like to first give the foundation information. There is very basic information that you need to have before you start balancing equations and writing chemical formulas. So if you do not have that basic information, even if I took you straight to balancing of equations and writing chemical formulas, I may not be of helpful. So let me take you through some basic information that you need to write. For you to be able to write the chemical formulas correctly, you must have the chemical symbols correct in your fingertips. So you should know, if you're talking about potassium, you should know that the chemical symbol for potassium is K. If I am talking about sodium, you should know it is Na. So the chemical symbols of any element you want to deal with, you must know it. The second thing you must have in your fingertips is the valence electrons. The valence of the element you are talking about. And that's what I want to take you through, how to determine the valence of an atom. And the other third thing I think you must have is the elements in the first 20 elements in the periodic table. So you need to master. You should know that the first one is hydrogen, helium, downwards to calcium number 20. So valence electrons are very, very critical in writing chemical formulas. Valence electrons are very important. Therefore, we want to define what a valence electron is. What is a valence? This is the number of electrons an atom loses or gains during a chemical reaction. Valence electrons are also called combining power, because this is what we use to combine atoms to form a compound. Combining power. Here I have a table that contains the first 20 elements, atomic number 1 to atomic number 20. I have the name of the element, the symbol of the element, the number of protons, electrons, and electron arrangement. We call it electron configuration. So the reason why I have this is that I want to show you how to get the valence of an atom, of an element. The valence. That is very important for you to know. First, as I have said, you must know that atomic number 1, we have hydrogen. Atomic number 2, we have helium. Atomic number 3, lithium. Number 4, beryllium. 5, boron, carbon, nitrogen. Atomic number 8 is oxygen. Atomic number 9 is fluorine. Atomic number 10 is neon. 11 is sodium. Magnesium. Number 12. Atomic number 13 is aluminium. Silicon is atomic number 14. Phosphorus is atomic number 15. Sulfur is atomic number 16. Chlorine, argon, potassium, and finally calcium, atomic number 20. Calcium. When you know the atomic number of an element, you automatically know the number of protons present. You automatically know the number of electrons present. As you can see, atomic number is equal to protons and electrons. So just get n atomic number 17. Atomic number 17 is chlorine. It means it has 17 protons and 17 electrons. Very important. So when we are writing electron configuration, if I pick 17, chlorine. I want to write electron configuration. I know that chlorine has 17, is atomic number 17. Therefore, it has 17 protons, 17 electrons. So when we are writing electron configuration, we are writing the electrons in the first energy level, second and third energy level. So chlorine has 1, 2, 3 energy levels. So you must make sure that this one will sum up to 17. 2 plus 8, 10, 10 plus 7 is 17. So we have two types of electron configuration. We have the duplet and the octet. So those elements like this, like helium, it has only electron configuration of 2. This one we call it a duplet, 2. But the rest, to be stable, they must have an octet. This one is called octet. This one is called octet, electron stability, octet. Very good. So what is the importance of electron configuration? Writing electron. If now I want to know the valence of carbon, I will get the electrons in the outermost electrons, and then I ask myself, carbon is not stable because it must have a stability of 2 or a 288 or a 28. If sulfur is atomic number 16, atomic number 16, 16 protons, 16 electrons, electron configuration is 2 to 8 to 6. How will it react? How does sulfur become stable? Sulfur has, we consider the electrons in the outermost energy levels, the outermost energy level. So sulfur has 6 electrons in the outermost energy level. So what will happen? Will it lose 6 electrons to be stable, or it will gain 2 to be stable? It is easier to gain 2 electrons, so plus 2, it will gain to have a stability of 288. It will gain 2, and it will become negatively charged sulfur. It will become negatively charged. When an element gains electrons, it becomes negatively charged, and when it loses electrons, it becomes positively charged. So what is the valence of sulfur? Is 2. So whenever you see sulfur, sulfur has a valence of 2. Calcium. Calcium is atomic number 20. It has 20 protons, 20 electrons. So when these electrons are written in the energy levels, the first energy level always starts with 2 electrons. So 8, 8, and then 2. This is 20. Look at what will happen. So 2 to 8 to 8 to 2. This is the electron configuration of calcium. So during a chemical reaction, this one is not stable. Calcium is not stable. Therefore, it will react by losing 2 electrons. Gaining 6, for it to have the stability of 2888, requires a lot of energy to gain. Therefore, it requires less amount of energy to lose 2. Therefore, it loses the 2 electrons and it becomes calcium 2 positive. So these electrons that are lost from an element or gained is what we call the valence electrons, and very important in writing chemical equations and balancing. Very good. So what I'm saying is that you must know the atomic number of an element. Once you have the atomic number of the element, you write electron configuration, and you shall be able to know the valence of that electron. Suppose I want to know the valence of aluminium. Aluminium is atomic number 13. Yes, aluminium, I know it is atomic number 13. Therefore, 13 is 2 to 8 to 3. This is 2, 10, 13. Atomic number, electrons, 13. Therefore, what will happen? Aluminium will react by losing 3 electrons to be stable. It will not gain 5. It will require a lot of energy to gain 5 to be stable. But it will require less amount of energy to lose 3, and then the ion, which is now aluminium ion, 3 positive, will have a charge, a net charge of positive. And this one is aluminium ions. So generally metals react by losing electrons, and non-metals react by gaining electrons. That is the general trend. So hoping that you have understood how to get the valence of an electron, now we can go ahead and talk about the elements which are not in the periodic table. So what about those elements which are not in the periodic table? We have few of them. We have elements such as zinc, that is commonly used and is not in the first 20 elements. We have copper, we have barium, we have lithium is not majorly used, so I want to debate the ones that are commonly used. Iron, we have iron 2, most compounds have iron 2. Which else? Zinc, copper, lead, very good, lead. So these 1, 2, 3, 4, 5 are commonly used. And what is the valence of this? You realize that all of them, they have a valence of 2. So zinc has a valence of 2, copper has a valence of 2, barium has a valence of 2, iron has a valence of 2, although we have iron 3. We have iron 2 and iron 3. But most compounds of iron, we have iron 2. Unless you are told lead is valence 2. So all of these, they have a valence of 2. They lose only 2 electrons to be stable because they are metals. So this should not be a problem. Whenever you say zinc, remember zinc has a valence of 2. Copper has a valence 2. Barium has a valence of 2. Iron a valence of 2. Lead a valence of 2. The next very important basic information I want you to have is about radicals. We have radicals which are used to form salts, which are combined with metals to form salts and other compounds. Therefore, we need to understand what a radical is and the valence electrons of each radical. What is a radical? Or radicals are these are groups of atoms with a net charge that exists and reacts as a unit during a chemical reaction. You don't need to radical valence electron. So we have those radicals in valence that have a valence of 1. We have the radicals that have a valence of 2 and the radicals that have valence of 3. But I don't think you have seen very many chemical reactions dealing with phosphorus. So this one is not commonly used. We want to deal with the commonly used. We have salts, carbonates, magnesium carbonate, zinc carbonate, magnesium sulfate, zinc sulfate. We have sulfites, sodium sulfite, we have the sulfite. So these are the commonly used radicals. We have the nitrates, magnesium nitrate, potassium nitrate, we have there. We have sodium hydroxide, calcium hydroxide. We have ammonium carbonate, ammonium sulfate. So the ammonium ion has got a valence of 1. So whenever you are using ammonia, remember it is valence 1. This one you must diagram, you must understand, you must read them regularly. Read it twice, thrice, 4 times, and these things shall get into your system. So once you know that hydroxide ion has got a valence of 1, nitrate ion has got a valence of 1, hydrogen carbonate has got a valence of 1, hydrogen sulfate has got a valence of 1, -1, then you will be able to see the way we are going. This one is very helpful in writing chemical equations or formulas. Carbonates has a valence of 2. That one, get it like that, master it like that. Sulfates have a valence of 2. What did I say? Carbonates have a valence of 2. Sulfates have a valence of 2. Sulfite has a valence of 2. Very important. So now when we come writing chemical formulas, you are going to find out how important the valence of radicals and other elements is in writing chemical formulas. So let us go straight now to writing chemicals. Is a chemical formula for sodium chloride salt. Let me write another one. If I write here magnesium chloride, I'm going to put it to here. But these two, I didn't put it for chlorine, for sodium chloride. But for magnesium chloride, I have a 2 here. So why did I do that? I know that magnesium is atomic number 12. electron configuration 2 to 8 to 2. Therefore, how does it react? It reacts by losing 2 electrons, so it has a valence of 2. Chlorine. Chloride ion is atomic number 17. Chlorine is atomic number 17. It has electron configuration of 2 to 8 to 8 to 7. Electron configuration of 2 to 8 to 7, yes. So during chemical reaction, what happens? It reacts by gaining 1 electron. Therefore, the valence of chlorine is -1. We don't write -1, we just write -1, negative. So 7 has shown me that the valence of chlorine is 1. So therefore, let me write 1 here, up here. So what happens during a chemical reaction? They interchange the valence electrons. So this one comes here 1, and this one comes here. And so therefore we have magnesium 1, chloride 2. But big 1, we don't put it like there. We assume it is there, but we just remove it. Therefore, the final product we have is magnesium chloride. And that's why magnesium chloride is written with 2, and this one is not. So let us see why sodium chloride, there is no 2 here. Sodium chloride is atomic number 11. So sodium is atomic number 11. Electron configuration 2 to 8 to 1. Chlorine, we have said, is atomic number 17. Electron configuration 2, 8, 7. How does sodium react? Sodium reacts by losing 1 electron to be stable because it cannot gain 7. Therefore, it loses 1 to form sodium ion positive. Chlorine, electron configuration 2, 8, 7, react by gaining 1. So if it gains 1, it becomes negatively charged. So negative, positive combine to form sodium chloride. So both of them, as you can see, they have a valence of 1, 1. So when we are talking about a valence, we don't care whether it is negative or positive. Valence, if it is 1, it is 1, not negative or positive. So sodium, valence 1, chlorine, valence 1. So they interchange 1. So they do like this. So 1, 1. So 1, 1 is like this, not there, or it cancels out. Therefore, sodium chloride. So this is the chemical formula of sodium chloride, and this is the chemical formula of magnesium chloride. Zinc nitrate, zinc sulfate. These are salts. So zinc sulfate is written like this, zinc nitrate is written like this. So let me first talk about the nitrate, and then zinc nitrate, and then sodium nitrate before I come to sulfates. Let me talk about nitrates. Nitrate, we know, is a radical. Nitrate is a radical, valence 1. Therefore, it means that this here, it has a valence of 1, right? Zinc, I have told you that metals which are not in the periodic table, all of them, they have a valence of 2. So don't think twice. Zinc, lead, copper, iron, take them to have a valence of 2. So it means this zinc has a valence of 2. So what will happen? They will interchange, cross multiply. So this one will come here, 2, and this one will come here, 1. So the final, let me read this, we will have zinc nitrate. Because this one we cannot put 2 here, we put a bracket to differentiate this one so that we cannot confuse, and we have 2. And this one is called zinc nitrate. So let me write zinc or potassium nitrate. Potassium nitrate is KNO3. That is potassium nitrate. Do you realize I don't have a bracket here? I don't have a bracket. Why don't we have a bracket there? We know that potassium is atomic number 19, electron configuration 2881, therefore it has a valence of 1. A nitrate, we know it has a valence of 1, which is negative. but we have told you for variance we don't care whether it is negative, it is 1 1. So what will happen is that this one will bring 1 here and this one will bring 1 here. So 1 1 is like it is not there, and therefore the chemical formula for potassium nitrate is KNO3, as simple as that. But if it is magnesium nitrate, so if you write magnesium nitrate like this and leave it like that, you will be wrong. You have not considered the valence electrons of each of them. Magnesium is atomic number 12. Atomic number 12. So electron configuration 2 to 8 to 2. And nitrate has a valence of 1. That one you must master. Nitrate has valence 1. So what happens? So magnesium is valence 2. Nitrate is valence 1. So 1, 2. So therefore the final magnesium nitrate is MgNO3 bracket 2. And this is the correct formula for magnesium nitrate. Magnesium nitrate. So we have a nitrite and a nitrate. So when it is 3, it is nitrate. Nitrate. When it is 2 here, when we have 2 here, it is called nitrite. Let me come to sulfates. Zinc sulfate. Remember the sulfate has a valence of 2. The sulfate has a valence of 2. Zinc has a valence of 2. So you put 2 here, put 2 here. So you cross multiply, we have 2. You cross multiply, we have a bracket, and then we have 2. So these 2 and these 2 cancels out, and then the final chemical formula for zinc sulfate is ZnSO4. Like that. So what about zinc nitrate? Sodium sulfate. Sodium sulfate. Sodium sulfate, if you write like this, you will be very wrong. You will be very wrong. Sodium sulfate, so the sulfate itself here has a valence of 2. The sodium is atomic number 11, 281. Therefore, it has a valence of 1. So this one transfers 1 here, and this one brings 2 here. So the chemical symbol for sodium sulfate is Na2SO4, and this is sodium sulfate. You can see it is different from zinc sulfate. Zinc sulfate does not have 2 here. It doesn't have anything there. Therefore, valence electrons are very important in balancing equations. The next one, let us talk about the carbonate. Sodium carbonate. If you write like this, you will be very wrong, because the carbonate has a valence of 2. Sodium has a valence of 1. So when it interchange, this one happens. So sodium will have 2, and the carbonate will be like this. This one is sodium carbonate. Yeah, so what about the calcium carbonate? Calcium is atomic number 20. Carbonate. Atomic number 20, it has a valence of 2. The carbonate has a valence of 2. So 2, 2, put 2 here, put a bracket, put 2 here. So these 2 and these 2 cancels out. So therefore, the final calcium carbonate chemical formula is calcium carbonate. So once you have known these things, writing and balancing chemical equations will be very, very easy once you have understood what we have dealt with. The next one is ammonium ion. So ammonium ion is valence 1. Ammonium ion has got a valence 1. So if I want ammonium nitrate, we will have ammonium nitrate. This one has a valence of 1. Nitrate has a valence of 1. Therefore, the correct chemical formula for ammonium nitrate is just like this. Ammonium nitrate. And this is very correct for ammonium nitrate. It is fine. But what if I wanted to write ammonium sulfate or ammonium carbonate? So ammonium carbonate, I know the carbonate has a valence of 2. I know this nitrate, the ammonium has a valence of 1. Whether it is positive or negative, it doesn't matter. The thing is 1 or 2 or 3. the variance. So what happens, this one they would exchange. Because there is 4 here, we must have a bracket here to put it 2 here. This 1 will come here, 1. 1 has no effect, therefore the correct chemical formula for ammonium carbonate is NH4 bracket 2CO3. That is the correct chemical formula for ammonium carbonate. Ammonium sulfate is the same, like this. So ammonium sulfate is H4 bracket 2 sulfate. Because the sulfate has a valence of 2, ammonia has a valence of 1, ammonium ion has a valence of 1, so no, like that. Suppose I wanted to write aluminium oxide. Is this the correct chemical formula for aluminium oxide? You would be right. You have aluminium, you have oxygen, so that's an oxide of aluminium. But now, once you have written aluminium oxide, you want to write aluminium like this, you want to write aluminium oxide. Once you have written like this, now you ask yourself, what is the valence of aluminium? What is the valence of oxygen? So you already know that aluminium is atomic number 13, 2 to 8 to 3, so the valence is 3. You know that oxygen is atomic number 8. So the electron configuration is 2 to 6, so it will gain 2 electrons, so the valence is 2. So when now you have aluminium 3, oxygen 2, what happens is that this one will bring 2 here, and this one will bring 3 here. Therefore, aluminium oxide is 2 oxygen 3. And this is the correct formula of aluminium oxide. Suppose I want to write aluminium sulfate. Aluminium sulfate, if you write like this, initially you are fine, you are okay. This is aluminium sulfate. Now the only thing is that you have not asked yourself, what is the valence of the sulfate? What is the valence of aluminium? Aluminium is valence 3. We have said that. The sulfate is valence 2, right? So what happens is that aluminium, the sulfate, they interchange. This one comes here, 3, and this one comes to here, 2. So the correct formula for aluminium sulfate is aluminium 2 sulfate, and then you put a bracket there, 3, and this is the 4. Aluminium sulfate is written as that. Thank you. Let us meet in the next video for balancing chemical equation. So next, good day wherever you are. Today I want to take you through a very important salt in chemistry we call salts. First I want to define what a salt is, and once we understand a salt, and then we will be able to understand how important this topic is. What is a salt? A simple definition, we know that a salt is a substance. A salt is a substance that is formed when the hydrogen ion or ions in an acid, hydrogen ions in acid are either wholly or partially replaced by a positive ion. That is the definition of a salt. So somebody could be wondering, now what does this mean? Let me give you an example of what a salt is. Take an example of a reaction between a base and an acid. For example, sodium hydroxide plus Let me take sulfuric acid. This is a base plus an acid. What do we get? We get a salt plus water, neutral substances. We get a salt plus water. So which salt do you expect here? It is sodium sulfate. Sodium sulfate plus water. What is this? A salt, and this is water. Now what is a salt? A salt is a substance that is formed when the hydrogen ions in the acid, what is this? Is the acid, and this is the base. Now look at this acid. The hydrogen ions in the acid has been replaced. Is it to replace or displace? Has been displaced. So the cation from the sodium ion has displaced or has replaced the hydrogen ions in the acid. So when the positive ion replaces the hydrogen ion in an acid, a salt is formed. Very correct. Even take an example, even a metal, sodium plus HCl. What do we form? We form sodium chloride. This is a metal plus hydrogen gas. This one is a metal, this one is an acid, and this one is a salt, this one is a gas. We are concerned about the salt because we are talking about salts. The salt sodium chloride, how was it formed? What is a salt? It's a substance that is formed when the hydrogen ions in the acid are wholly or partially replaced by a positive ion. So here the positive ion is, remember, sodium. Sodium is positively charged. Let me dismantle this one, hydrogen ions plus chloride ions. So this hydrogen, positive ion here displaces the hydrogen ion in the acid. So this sodium attaches itself to chlorine and they form the salt. So we are going to form sodium chloride. So the hydrogen ions in the acid has been displaced, has been replaced by the sodium ion, which is positively charged, and then a salt is formed. So a salt is a substance that is formed when the hydrogen ions in an acid are wholly or partially replaced by a positive ion. We have different types of salts. We have actually 4 types of salts. We have number 1, the normal salt. A normal salt is a salt which does not contain any replaceable hydrogen in it. Salts such as sodium chloride, sodium sulfate, calcium nitrate, all of these are called normal salt because they do not contain the replaceable hydrogen in them. They don't have replaceable hydrogen in them, so they are called normal salt. Number 2, we have acid salts. It is important for you to know that acid salt, these are the salts which contain replaceable hydrogen in them. So they contain hydrogen in them. An example of this is sodium hydrogen carbonate. Sodium hydrogen carbonate is an acid salt because it contains a replaceable hydrogen in it. Another example is potassium hydrogen carbonate. Potassium hydrogen, or even carbonate or sulfate. Also, this one contains the replaceable, therefore this one called acid salt. They are called acid salts. Number 3, we have basic salts. What are the basic salts? These are salts that contain hydroxyl ions in them, OH negative. So those salts that contain hydroxyl ions in them, they are called basic salts. An example, e.g., we can give zinc, basic zinc chloride. This one is called basic zinc chloride. That's one pattern example. And then last, number 4 is the double salt. Double salt is a salt in which there are two different anions and cations. One salt contains it can have two cations in it and two different anions in it. An example of a double salt, you can talk about potassium aluminium sulfate. This one is called potassium aluminium. This is potassium, this is aluminium, and then sulfate. That one is a double salt. But my major aim is to enable you to know the types of salts. So it is important to know types of salt and at least one example for each. The next thing I want to talk about is the solubility. Solubility of salts. Now this is where you really need to understand solubility of salts. Salts that are soluble in water and the salts which are insoluble in water, it is important for you to understand them. But before we talk about the solubility of salts, it is important for you to know the types of salts we have. We have salts that we call nitrates. Number 1, we have salt that we call nitrates. Example is calcium nitrate, potassium nitrate, sodium. Type of salt number 2 is the chlorides. So when I'm talking about chlorides, you should know examples of chloride. We have magnesium chloride, zinc chloride, we have sodium chloride, etc. So chloride is an example. These are examples of chlorides. And then number 3, we have carbonates. We have magnesium carbonate, we have sodium carbonate, etc. Every metal carbonate, every metal at least has each of every salt I'm talking about, except some metals which does not have some salts, but it is few of them, very few of them. Number 4, last is the sulfates. So sulfates, we have several of them. You can start from copper sulfate, we have zinc sulfate, and it is so many of them, etc. There are so many other sulfates. So once we have now known that we have 4 types of or different salts, we have 4 different salts: nitrates, chlorides, carbonates, and sulfates. So for you to mention a nitrate, you put the metal in front: magnesium nitrate, calcium nitrate, potassium nitrate, sodium chloride, zinc chloride, like that, sodium carbonate, etc. Now we will go straight away and see the salts which are soluble in water and those that are not soluble in water. Very important in practicals and answering general questions in chemistry. The question is, are all these salts we have mentioned soluble in water? No, not all of them are soluble in water. So we will start with nitrates. All nitrates, all of them, all nitrates dissolved in water are soluble in water. So all of them, when you dissolve them in water, they form a soluble salt. Chlorides. Are all chlorides soluble in water? No. All of them, all chlorides are soluble in water, except, here I want you to mark that, except the chloride of silver, silver chloride, comma, lead chloride, the chloride of lead or lead, are insoluble in water. So lead chloride, silver chloride, they don't dissolve in water. They form a white precipitate when you put them in water. But the difference between lead chloride and silver chloride is that lead chloride dissolves in hot water. When you warm the water, or when you warm the white precipitate of this, it will dissolve to form a colorless solution. Therefore, lead chloride is soluble in hot or warm water. Very important. So all chlorides, they are soluble. They dissolve in water, forming a colorless solution, except silver chloride and lead chloride. Sulfates. All sulfates are soluble in water, except, mark this, except which one and which one? Except lead sulfate, lead sulfate, barium sulfate. These two are completely insoluble in water. But calcium sulfate is insoluble in cold water. It's so insoluble, but it is just slightly. So this one is slightly soluble. But if you dissolve calcium sulfate in water, it forms a white precipitate, but it is slightly dissolved. But so we say calcium sulfate, lead sulfate, barium sulfate are insoluble in water, because the water, if you dissolve this one, you will see some milk. So if it is milk, then that one is not a colorless solution. So calcium sulfate, lead sulfate, and barium sulfate, they form a white precipitate. It means they are insoluble in water. Finally, the carbonates. Carbonates. All carbonates are insoluble, meaning that all carbonates do not dissolve. They don't dissolve in water. Instead, they form white precipitate. They form milky solution. They don't deform. All of them, they are insoluble, except. That's why I told you the word except. Those that are exceptions are the most important you want to, because they are the one that are being tested. So all carbonates are insoluble except the carbonates of potassium, potassium carbonate, sodium carbonate, and ammonium carbonate. These three, ammonium carbonate, sodium carbonate, potassium carbonate, all of these three are soluble. They dissolve in water, forming a colorless solution. Very important to know that. So when we are going to prepare salts, before you prepare salt, you must know, is this salt I'm preparing soluble or insoluble? Very critical. Another small thing I want to talk about is the solubility of bases. You need to understand that what are the bases? What is a base? when we react a base plus an acid, a neutralization reaction, what are the bases? So metal oxides, or most of the metal oxides are insoluble bases. So a metal oxide is a base, but most of them are insoluble. They don't dissolve in water to form a solution. Soluble bases such as sodium hydroxide, so hydroxides, calcium hydroxide, magnesium hydroxide, all of these ones are called soluble bases. They are the bases. So our base, hydroxides and metal oxides are bases. Very important. It is important to note that. So when you hear a neutralization reaction is a reaction between a base and an acid that gives you neutral substances, that is salt and water, as the only products. So having given the basis of the salts, we have defined the salt, we have talked the type of salts, and then we are talking about solubility, that all chlorides are soluble except the one we have said. So we want the basis of the importance of what we were doing there is this subtopic of methods of preparing salts. So before you prepare salt, you need to understand and be aware, is the salt I'm told to prepare soluble or insoluble? So preparing salt depends on the solubility of a salt. It depends on solubility of a salt. So we have around 7 methods of preparing salts. I want to mention, just mentioning them. We have acid plus metal reaction, which will give us salt plus water. This one is used to prepare acid plus metal, it is salt plus hydrogen gas. So this one is used to prepare soluble salts. If a salt is soluble, and then this method can prepare. I can prepare magnesium chloride, I can prepare zinc chloride here directly, because those are soluble salts. Method number 2 is acid plus insoluble base. Insoluble base ni magnesium oxide, copper oxide, copper 2 oxide, lead 2 oxide. So those are insoluble bases. So we will form salt plus water, and the salts formed here, they are soluble. Number 3, we are going to mention acid plus soluble bases. Soluble bases, mostly they are hydroxides, so they will give soluble salt. And number 4 is acid plus carbonates. An acid plus a metal carbonate will give you salt, water, and carbon dioxide. The effervescence is expected. Therefore, this one also is used to prepare soluble salts. Number 5, we have acid plus metal hydrogen carbonates. Metal hydrogen carbonates will also give you salt, carbon 4, and water. Therefore, it is a soluble salt. I said I want to just mention methods of preparing salts, because my major aim is to show you how to prepare the salts and not. The 6th one is direct synthesis. It can also prepare soluble salt. Direct synthesis can also prepare soluble salts. Direct synthesis can also prepare insoluble salt. Direct synthesis is the direct combination of elements. For example, a metal plus an non-metal, like sodium plus chlorine will give us sodium chloride. So this one is direct synthesis. So this one is soluble. It can also prepare insoluble salt. So direct synthesis, direct combination of elements can prepare both soluble and insoluble salts. And then finally, number 7, this is where my major concern is the precipitation reactions. This one is what we call the double decomposition. It is a type of reaction which occurs, and the salts that are formed here are insoluble. So this is the major method that is used to prepare insoluble salts. Very good. So before we embark on answering the questions, I want you to understand something in the reactivity series. In the reactivity series, we have potassium as the most reactive metal, followed by sodium, calcium, magnesium, aluminium. Then we have an non-metal, carbon. So carbon is very reactive than zinc. And then my concern is hydrogen. Hydrogen is more reactive than iron, than lead, than copper, and mercury, silver, and gold. Therefore, what it means, the reason why I'm showing you this is because you cannot react, for example, HCl plus iron to form iron 2 chloride. You cannot react directly lead plus nitric acid to form lead nitrate. If you are asked, starting with lead, describe how to prepare lead nitrate, there is no way you are going to say that add nitric acid to lead. Why? Because lead ions cannot displace the hydrogen here, because lead is less reactive than hydrogen. You understand that? So we are not going to, therefore, in this case, you must react lead with oxygen to form lead oxide and then react with nitric acid. Now you must make it an oxide. Very important. Therefore, this reactive series is important for you to understand that all metals that are above hydrogen, you can react with acids directly and form the salts. You can react them with the acids directly and form the salts you want to form. But metals below hydrogen, iron, lead, copper, you cannot react with acids directly to form salts, because the metals cannot displace the hydrogen in the acid, because they are less reactive than hydrogen. You are provided with solid potassium hydrogen carbonate. Describe how a solid sample of potassium nitrate can be prepared. So we are preparing potassium nitrate. First, ask yourself, is potassium nitrate soluble or insoluble? It is soluble. Therefore, we can react directly nitric acid with potassium hydrogen carbonate to form potassium nitrate. So you start by add excess potassium hydrogen carbonate into a beaker containing dilute nitric 5 acid. Nitric 5 acid. So because you have added potassium hydrogen carbonate in excess, you have to filter so that you can remove the excess. So the next one is to filter to obtain excess potassium hydrogen carbonate as the residue. Another term here we need to understand is the filtrate and the residue. When you are doing filtration, whatever that is remaining in the filter paper is called the residue. The solution that gets over or that goes through the filter paper is what we call the filtrate. So it is important to understand these terms when you are preparing salts. So filter to obtain excess potassium hydrogen carbonate as the residue, and then now we want the solid. So we have now to evaporate the filtrate, which is potassium nitrate. The filtrate is potassium nitrate, of course. So we are going to evaporate that. So evaporate the filtrate to saturation. And allow the saturated solution to cool to form crystals. So by doing this, you would have obtained the solid sample of potassium nitrate. Next one, starting with copper, describe how a pure, mark that, sample of copper 2 carbonate can be prepared. Question 1, you ask yourself, is copper 2 carbonate the salt that you are supposed to prepare soluble or insoluble? Remember, all carbonates are insoluble except potassium carbonate, ammonium carbonate, and sodium carbonate. So since this one is not sodium, it is not potassium, it's not ammonium, it means it is insoluble. So this one is insoluble. So we need to know the method we are going to use. Then obviously we are going to use the double decomposition. So we are starting with lead. We are starting with copper. You cannot react copper directly to get copper 2 carbonate. Therefore, since copper is below the reactivity series, we cannot react copper with hydrogen with nitric acid to form copper 2 nitrate. We need copper 2 nitrate. But you cannot react copper plus nitric acid. Why? In the reactivity series, copper is below hydrogen. Therefore, what we do, you heat this one to form the carbonate. So heat copper metal in air to obtain copper 2 oxide. Very correct. So once now you have copper 2 oxide, now you add warm nitric acid, because actually oxides are insoluble, therefore you need to warm the acid. Next one is to add excess copper 2 oxide to warm dilute nitric acid. This acid could be in a container, in a beaker, so in, or you can say in a beaker, right? So what have you made? You have made now copper nitrate. We need copper nitrate first. We need that copper nitrate. So since we have in excess copper 2 oxide, we need to filter to obtain the copper nitrate only. So beaker and filter to obtain lead, not lead, but to obtain copper, to obtain copper 2 nitrate, to obtain copper 2 nitrate. Now we have copper 2 nitrate. What do we do with copper 2 nitrate? Since this one is a solution, since this copper 2 nitrate is a solution, we need a soluble carbonate so that when we react, we mix the two, they will interchange the anions and the cations to form lead, to form copper 2 carbonate, Therefore, we have now the filtrate to obtain this as the filtrate. So next, to the filtrate, add sodium carbonate. Remember, sodium carbonate is soluble. Add sodium carbonate solution. Right? Now, up to this form, we will precipitate out copper carbonate. To precipitate copper 2 carbonate, to precipitate copper carbonate. Now the white precipitate will be copper carbonate. Then what do we do? Because we want a solid copper carbonate, we filter the solution. Therefore, next is filter to obtain copper carbonate as the residue, copper carbonate as a residue. Because we were told pure, you need to wash it. Then wash the residue with distilled water, and then we dry, and then dry between filter paper. So up to that point, you have prepared copper 2 carbonate. A sample of water is suspected to contain the sulfate ions. Describe an experiment that can be carried out to determine the presence of the sulfate. I think this question is somehow misplaced because it's not part of the preparation of salts. So, but I can answer that. So, how can we tell somebody that this solution we have contains the sulfate? So, what you do, you add 3 drops of barium nitrate, to, if it is a test tube, to a test tube containing the sample of water that is suspected to contain the sulfate of water. Then followed by about 5 centimeters cube of 2 molar nitric acid, nitric 5 acid. So what will happen if a white PPT precipitate is formed? If a white precipitate is formed, insoluble, which does not dissolve, insoluble in the acid, sulfate, 2 minus sulfate ions are present. That's how you confirm for sulfate ions. A mixture contains ammonium chloride, copper 2 oxide, and sodium chloride. Describe how each of the substances can be obtained from a mixture. Now this is separation, but these are salts. That's why this question is here. Remember, these are salts. So how can you separate this salt? First, you need to understand that which salts are soluble. This one is soluble, this one is insoluble, this one is soluble, but also this one is a supplement. A substance which sublimes, changes directly from a solid to a gas. So how will you separate? I think that's why this question comes here. How can you separate these three, each of them, to obtain each of them without losing any of them? So let me give you the procedure on what to do. You put this mixture in a beaker. So place the mixture in a beaker. Covered with a watch glass containing cold water. You heat the mixture until no further change. So what will happen? Ammonium chloride subprimes with subprimes and condenses on the cold watch glass. The next, now we are left with copper 2 oxide and sodium chloride, but we know sodium chloride is soluble, copper 2 oxide is insoluble. Therefore, we dissolve this in water. So dissolve the remaining, or add water, or dissolve the remaining mixture in water. You dissolve the remaining mixture in water. So sodium chloride will dissolves, and copper 2 oxide does not. So what do you do next? You filter the mixture to get copper 2 oxide as the residue and sodium chloride as the filtrate. Now next one, now we want to get the solid from the filtrate sodium chloride. You evaporate the filtrate, to saturation, and allow the saturated solution to form form crystals. So these crystals are sodium chloride. You will get them. We have gotten this residue and we have this, and by that we have separated the 3 salts, each of them, without losing any of them. Iron 2 oxide was found to be contaminated with copper 2 sulfate. Describe how a pure sample of iron 2 oxide can be obtained. This one is your home work, so please do that, and if you get a problem, you will always consult me. It is always free. I don't charge anything for you to consult me, even if it is at night. It doesn't, I don't touch anything, so you can, if you have a problem, you will always find me. My contacts are always there. Starting with sodium metal, describe how a sample of crystals of sodium hydrogen carbonate may be prepared. We are starting with sodium metal. We want to prepare sodium hydrogen carbonate. So first thing you do, you react sodium metal with water to form sodium hydrogen carbonates. Therefore, react sodium metal with water to obtain sodium hydroxide. To obtain sodium hydroxide. So what will you do with the sodium hydroxide obtained? You bubble. Bubble is to pass a gas. Bubble into the solution. Bubble into the solution. Bubble into the solution. Excess carbon 4 oxide gas. Excess carbon 4 oxide gas to obtain sodium hydrogen carbonate. But we are asking to obtain crystals. So after now we have this solution, we need to evaporate. So evaporate the solution. Evaporate the solution to saturation. To saturation to form crystals. So once you have evaporated the solution, crystals are going to be formed, and we have obtained the crystals of sodium hydrogen carbonate. Oh, there is 3 here, sorry. There is 3 here, sodium carbonate. Starting with the copper tannings, describe how a sample of copper 2 sulfate crystals can be prepared. First, we ask ourselves, is copper 2 sulfate soluble or insoluble? Copper 2 sulfate is a soluble salt. The question is, why can't we react Cu plus sulfuric acid to get us copper 2 sulfate? And that story is over. Why can't we do this? The reason is simple. The reason is this. In the reactivity series, hydrogen is above copper, meaning hydrogen is more reactive than copper. There is no way you can react. There is no way copper ions will displace hydrogen in the acid to form the salt you want, because the copper ions is less reactive than hydrogen ion. Therefore, we need to now make this copper to form an oxide. Very important. That is the reason why we can. So you heat copper metal, heat copper metal in air to get copper 2 oxide. Now then you add dilute sulfuric acid, to the copper 2 oxide, to form. So add dilute sulfuric acid to the copper to form copper sulfate. Now we have the copper sulfate. Then what are we going to do with the copper 2 sulfate solution? Filter excess copper 2 oxide and evaporate the filtrate. Evaporate the filtrate to saturation. Allow the saturated solution. To cool and form crystals. To form crystals of copper 2 sulfate. We have prepared that. Quickly, let us look at the next question. Starting with barium nitrate solution, describe how a pure sample of barium carbonate can be prepared. So we are preparing barium carbonate. That's where our interest is, barium carbonate. Question: is barium carbonate soluble or insoluble? It is insoluble. So if it is insoluble, then you must always understand that that one will always involve a double decomposition kind of a reaction. So quickly dissolve sodium carbonate we are starting with barium nitrate. Okay, so we can start in a different way. Add water, not add water. So we have sodium, we have barium. This is the solution we have. So let us add straight. Add barium nitrate. Add barium nitrate solution into a beaker containing sodium carbonate solution. Filter to obtain barium carbonate as a residue. Wash the residue with distilled water. and then dry the solid between filter paper, papers. Remember, if we are preparing insoluble salt, we don't evaporate. We don't evaporate to obtain an insoluble salt. Nothing. We only evaporate to obtain crystals of a soluble salt. So what is happening here? We have barium nitrate. We are adding sodium carbonate. So what happens is that the cation this side will take the anion this side, and then the anion this side will take the cation this side, and they will form barium carbonate plus sodium nitrate, like that. And this one is a solid, this one is an aqueous. And this is the white precipitate, and this is the solid we want to form. Describe our sample of lead-2 sulfate, ammonium chloride, and sodium chloride can be obtained from a mixture of the three. That one is homework. Do that. If any problem, always contact WhatsApp. I will always respond to your problems without any delay. Starting with solid sodium chloride, describe our pure sample of lead-2 chloride can be prepared. I want also to give this one to you as an homework. This one we have already done it. Let me look at the next one. Describe how the following reagents can be used to prepare lead-2 sulfate. So we are preparing lead-2 sulfate, but we have been given as samples. We are starting with solid potassium sulfate. We are starting with lead carbonate, and then dilute nitric acid, and then distilled water. So we have been given the reagents to use. We are preparing lead sulfate. Lead sulfate is insoluble. So if it is insoluble, the reaction is double decomposition. There's no another. If we are preparing an insoluble reaction, we must use the precipitation reaction. We are precipitating out a white precipitate. So first, let us dissolve the potassium sulfate in this water. So dissolve the potassium sulfate in distilled water to form potassium sulfate solution. The next is to react the carbonate with what's carbonate, the react red carbonate with dilute nitric 5 acid to get lead nitrate. Now we have lead nitrate solution and we have potassium sulfate solution. What do? We mix the two solutions. Mix the two solutions. Mix the potassium sulfate solution and lead nitrate solution to precipitate lead sulfate. The next one now, since we have formed lead sulfate, which is an insoluble salt, we filter filter, filter to obtain, filter the mixture, to do what? To obtain lead sulfate as the residue, and as the residue. Then what is next? Because we wanted is it pure, we have used to prepare ready to sulfate, so there is no need of washing. We can leave at that point. So filter the mixture to obtain lead sulfate as the residue, and that is all. We stop at that point. If we are asked that to prepare pure, we need to wash it. If we were asked to give a dry solid, we need to dry it, but here we are not asked to dry it, so we can stop there. You are provided with water, lead carbonate, dilute nitric acid, solid sodium chloride. Describe a very clear step by step on how to prepare lead chloride. Homework. Do it, and I will mark for